Okay, welcome everybody. Before we start, who here is eligible to vote? It's not a lot of you. Who of you guys did vote? Okay. So no reason to cancel class to let you guys go vote. I think it's much. So please go, and if you haven't already, there is at the Marriott Library you can vote, and you can also still register to vote there. Okay, so today we'll talk about graphs. We'll do a quick recap of what we talked last time, and then move on to matrices. And we should be done with this fairly soon. And then I have like a longer critique and redesign exercise for the remainder of the class today. Any questions about projects, organizational from any other form before I get started? Yeah.
If we still haven't heard from our TA.
Oh, that shouldn't happen. Yes.
Okay.
Talk to me later.
Okay.
After class.
Do we know when we'll have grades for Project 5 in the midterm?
Midterm, hopefully soon, but it's like still crazy for me. Project? Homework 5.
Homework 5.
This week. But I'm trying to get the midterm done soon too, but I'm teaching 5 days a week and it's really hard to find the time to sit down and grade 70 exams. Yep.
So we have reached a situation with a project where we have the front end and some mock-up data, but we haven't been able to implement the database.
Implement the database?
Yeah, because we're working with like dynamic data that's retrieved from the database.
Mm-hmm.
And if that's part of our proposal, but what we eventually turn in is just using the mock-up data.
That's fine. I'm happy to talk to you after class in detail, but generally I don't care too much on like how you handle the back end.
Okay.
So if you have a reasonable subset that still enables you to do whatever you want on the front end, then that's fine. Any other questions about projects or class organization? Next, on Thursday I'll talk about maps, and then we'll go into like a series of guest lectures. Basically, I will not be lecturing myself a lot after this week. Okay, so graphs. So we talked about the various applications of graphs, that you, like a road network is of course a graph, searching the shortest drive from A to B is a path task in a graph. Graphs are important in integrated circuits, in social networks, they're in biology and so on. We talked about this idea that the graph theory, it was founded in, based on this Königsberger Bridge problem in 1736. Here the question was whether we can trace, whether we can find a walk that crosses each of these bridges exactly once, but not more than once. And so it turns out that this is a problem that you can simply do as a graph. It doesn't matter what the geography of the individual landmasses is. All you care about are nodes and edges, where the nodes being the landmasses and the edges being the bridges. And so for this particular example, we also learned that it's not possible. More formally, like we talked about graphs being a set of nodes and edges, or vertices and links. And graphs in a network are very often used interchangeably as terms. If you make a distinction, it's usually that networks are something specific, like a specific network data set, versus graph is more the theoretical concept. A couple of terms that we introduced: a directed graph distinguishes between edges that go from A to B and edges that go from B to A, whereas an undirected graph, there's simply an edge connecting the two without any direction. Then we talked about trees. Trees are graphs with one specific restrictions. They do not have any cycles. So this here is a tree. What is also very common for a tree is that it has a defined root. And so in this example here, we have a defined root, and we can also recursively define a tree such that it has a root and 1 to n or 0 to n subtrees. We talked about a couple of graph measures. One of them was the degree. And the degree is essentially counting the number of edges that the node has. And if you have a directed graph, you separate between an in-degree and an out-degree. And degree is a measure of local importance. So, for example, here, Muriel in this graph has a pretty high degree, but she's not very central to the network. Whereas we have another measure between the centrality, which measures how many shortest paths go through a specific node. And here you can see that Muriel still has like a high value, but not as high compared to, for example, Valjean as it has in degrees. So here, well, Valjean, Muriel, looks like Muriel is a little bit bigger in proportion to Valjean than here. We talked about path and distances. A path is a route along links. So here are two different examples. The one here is not the shortest path, but just a general path. And here we have a shortest path from, or two shortest paths from 1 to 7. They're of equal length. Okay, so that was like a quick recap of the graph fundamentals, and now quickly about graph visualization. I distinguish between two different types of tasks and goals. These are the attribute-based tasks and the topology-based tasks. So attribute-based tasks are tasks that are concerned mainly with the attributes of the nodes or the links. For example, like how old are the people in the social network that I'm looking at, or what is the profession of the people in the social network that I'm looking at. Whereas topology-based tasks are concerned mainly with the connectivity of the network. So, like how is actor A connected to actor B, and so on. And then we introduced 3 different types of graph representations. We only talked about explicit last time, and today we'll talk about matrix and implicit. So explicit layouts are the most familiar type of graph layouts. They are these node link diagrams. So here, like we see, we have 5 different nodes and then links between them. So this is like a vertex, or a node is a point, and an edge is a line or an arc. And so we distinguish further between 3 different types of node link representation: free, styled, and fixed. The difference here is that free has a completely free arrangement of the nodes, so we can place them wherever we like. We can vary position, which is of course the most valuable visual channel. Styled layouts have some pattern of arranging these nodes, for example, in a circle or in a grid here. And fixed layouts have some given position for the nodes, and we only can basically adjust how we render the edges. And that's like a classical example for that is networks on top of maps. When we try to create a good graph layout, we have these various optimization criteria. For example, we want all edges to be of uniform length. We want to avoid edge crossings as good as possible. We want to optimize space, and so on. However, these criteria usually conflict. So for example, here we have a crossing-free graph, but we have one long edge. Here we have a uniform edge length, but we have a crossing. So it's not, there is no perfect solution based on these criteria, and there are of course many of them, and I'm sure you can derive some yourself. Then we talked about force-directed layouts, which we also talked about when we talked about D3. Here the idea is that this is a physics model where the edges correspond to springs and the nodes repulse each other. And so based on this physics simulation, we get these layouts. We talked about that this is computationally pretty expensive. It's O n to the power of 3, and the reason why you asked last time why it's to the power of 3, it turns out that it is the number of iterations that you need to get a stable layout corresponds to n. And so that's why it's n to the power of 3. And what that means is that it is not you cannot do this for large networks. However, you don't really want to do that for large networks because you get these giant hairballs, and I have this cat picture in here. And so these giant hairballs are not, they don't really help you solve a specific task other than wooing people with a cool picture and saying, okay, my data is big. We talked about styled layouts. Here, like you can see that this is pretty dense already, even with only 3% or 6.3% of all possible edges. And it's also easy to imagine that if I have a pattern in here, that the node ordering is important. So that I, for example, have local connections preferred over global connections. One approach to deal with these kind of edge problems is hierarchical edge bundling, where we kind of use the hierarchical structure of a data set that we potentially have to kind of draw a virtual tree connecting the various elements in a styled layout, and then we can route the links along those lines. And so here are a couple of examples that vary this beta factor that defines the bundling strength. And then I briefly also mentioned that you can also do this with, without a hierarchical structure by using a force-directed approach on edge segments, which is usually not as, well, computationally, again, very expensive and usually not as effective. Here is one of these examples with a force-directed layout for a fixed layout. And so there's not much to say about fixed layouts other than they are hard to make nice and that you basically need to use a lot of interaction to make them accessible. And so basically the recommendation here is if you have a data set like this, really think about whether you need to explicitly represent everything in its exact geographic location. And we'll talk more about this when we talk about maps. Then we talked about the special case of a graphed tree. We looked at tree comparison and these Rheingold-Tilford layouts, which are the basic tree layouts. Again, this is not something that I need to go into detail about. So if we revisit the explicit representations, what are the benefits and the disadvantages of them? First, the benefits is that they're able to depict all graph classes. They can be easily customized by weighting layout constraints, and they're really well suited for topology-based tasks. So it's easy for me to visually trace a path through a node link diagram. They're computationally very expensive to create good layouts. Even heuristic layouts are slow, and it tends to clutter. We have these like giant hairball problem. Then next we talked about multivariate graphs, where we try to find the compromise between the topology of a network and the attributes about them. So for example, the attributes can actually influence the topology, and so we need to see these two together. And the challenge here is that we need to support two central tasks, the topology itself and the attributes of the nodes. So if each of these nodes here has like a vector, how do we show this on top of this network while we still can actually show the topology? And so, well, I can skip over this. Here are a couple of approaches to do that. None of them is really great. Here are little pie charts. These bar charts, of course, they work for a limited number of attributes, similar to these line graphs or these bar charts with error plots. For categorical data, it's easy, just use node labeling, node colors as labels. But generally, like if you have a larger vector, you have to think about one of the next three approaches, either using small multiples, so where we have the same graph laid out and different experimental data mapped on top of it, or using data-driven node positioning. This was this example graph dice here, where we show, essentially, define a fixed layout based on attributes. So here we put each of the nodes exactly on the coordinates as given by the scatter plot and add the edges on top of it. This is of course only interesting or only valuable if you can transition easily between various attributes, and maybe even, which is not the case in this particular paper, but it would also be nice to transition to a force-directed layout, for example. And then I mentioned this piece of work that I did in the past, where like one of the ideas of doing multivariate network exploration is that you let the user decide which part of the network is really important to you right now, then extract this part of the network and then visualize like linearized attributes about them. So here we could, for example, divide the data set up into groups, show multiple data set, everything associated with this one particular node or with this cascade of nodes in this case. So a multiple view approach where you try to like preserve some of the topology in a second view. Okay, so this was the recap. Now let's talk about matrix representations. So matrix representations, instead of taking a node link diagram, they use an adjacency matrix. I'll let you take a look at this picture and think a little bit about this. So these matrix diagrams, essentially, we have the nodes here, both in the, this is like there's some layout problem. This is, of course, E is down here. The nodes here are represented as the rows and the columns in this matrix, and an edge is filled, a cell is filled in if an edge connects those two nodes. So if we take a look here, A does not connect to itself, so there is no A to A loop, so this is why this is empty. A does connect to B, as we can see here. A does connect to C, as we can see. A does not connect to D and does not connect to E, as this is also consistent here. How would this look like if we had arrows, like directed edges here?
We would have half the number of the cells that we have.
That's correct. And like, what would be, how could I distinguish for directions?
It would be asymmetric so that you pick starting nodes to be the rows or starting nodes to be columns.
Exactly. So I have to introduce a convention for the directionality. I could say the direction always goes from the columns to the rows, or from the rows to the columns. And then in this case, as you can see here, this matrix is perfectly symmetric. It wouldn't be if I had a directed graph. These matrix representations, they can be a little bit tricky to read. So for example, try to find the path from A to E only looking at this network. What do you have to do?
Do we know the order of column rows?
What do you mean?
Like, are we assuming it's directed or undirected?
Undirected.
So you just see at the intersection of A to E and E to A.
But I don't see a path from A to E. They're not directly connected. And if I wanted to find the path from A to E, what would I have to do?
You have to like recursively check each.
Exactly. So I basically can go from A to B. Okay, it's not connected to A, so I can look at the next node. And from B, I can then look, is B somehow connected to E? No, it's not. Then I can go to C, look at C, is somehow connected to E? Yes, it is. So I have to really, essentially try mentally and go through this. Like I always like to say, I sit down with a pencil and trace what a path is. So what does this tell us for how great those things are for realizing topology, or for doing topology-based tasks?
What's
So it'd be N squared.
N squared? The size of the, yes, matrix is N squared.
Search
But-
through it,
Yes.
even.
Yes, if you do it in a naive implementation, yes. But I meant mentally, not computationally. Sorry, if that wasn't clear.
It's not a good visual representation.
Exactly. It's not a good visual representation for path tracing, for example. It is, however, a good visual representation for certain topological structures if you learn to read them. So here are examples for topological structures. This, one column here corresponds to a star. This completed triangle here corresponds to a directed, a completely connected but directed graph. Then we have this cluster here. This is a bipartite graph. So we can, if you work with them a lot, you can learn patterns, and then you can identify them. And there are a couple of interesting papers. Well, let me first say about the node. As in any matrix, the order here is important. And you can always, this is not necessarily, these layouts, they don't have to be, you can vary them a lot. Like if I shuffle, for example, E down here, it's still the same. But I can try to vary the order of these matrices to allow certain tasks. So this is the example of the path tracing, which I kind of explained already. So here, the goal is from A to E to Z. So you would have to go through something like this. Here is another example of how these structures look like in a node link diagram versus in a matrix diagram. So we have cliques here, completely connected components, which are easy to spot. Bi-cliques here in green, which are also like easy to spot when you know what you're looking for. Tightly connected clusters, so we don't have like a specific pattern, but we can see that there is a group of nodes that are tightly connected. And as always, as matrices, order is critical. So this is the Leibniz-Arabin network, and if you look at it, if we sort it by name alphabetically, it's not very helpful. If we sort it by cluster, they can pretty much see these clusters of where those people interact, and then we can see like the very central nodes to this network, like Valjean here. He is connected to many of those clusters, and then here Gavroche is one of the other main characters. He's also very connected. So we see these lines for very central nodes, and we see these like dense clusters here pretty easily. But of course only when we have proper ordering. So there's another, like if we order here by frequency, which is simple, this is less obvious. So there is papers and libraries even for D3 out there that implement, like if you ever want to do something like this, there's a library, Reorder.js, that does, that comes with a lot of these reordering algorithms that are optimized for various tasks. Okay, so if you wanted to recap on matrix representations, one advantage of them is that they can represent all graph classes, so directed graphs, undirected graphs, and so on, but not also trees, but not hypergraphs. What they do is they put the focus on the edge set, and not so much on the node set. So, for example, if I have edge weights in a matrix layout, then I can easily encode the weight of an edge by, for example, using saturation or value. It is really simple to render because it's just a grid, right? I can, like, it's trivial to render. There is no elaborate layout algorithm. It's not computationally expensive to do this. Well, it's well suited for attribute-based tasks at edges via coloring the matrix cells to some degree. It is well suited for neighborhood-related topology-based tasks. So, for example, if I just want to understand the neighbors of one particular node, that is easy to do. One of the negative aspects of it is quadratic string space requirements. So from this follows that they are pretty usable or pretty useful if you have a very densely connected network. Because like when you have a lot of edges, you use the space anyways, no matter whether there is an edge or not. So if you have a very dense network, you can show that easily in a matrix layout. And they're not suited for path-related topology-based tasks as the downside of it. So here is a special case for kind of like almost a tree for genealogy with a this is like an example of a Simpsons genealogy. We have Jacqueline and Clancy are the parents of Patty, Selma, and Marge. Marge and Homer are then the parents of Bart, Maggie, and Lisa. And I'll show you the video here.
Dataset based on a layered matrix representation. This representation has no crossings, which makes it more scalable than the traditional genealogy visualizations. For example, here is a genealogy of 700 individuals presented by gene equals, and the same genealogy represented by a node link diagram. Let's start with a simple genealogy of the Simpsons TV series. The basic elements of the gene equals visualization are generations, individuals, male and female, families, and relationships within families. By family, we refer to nuclear families consisting of two parents and their children. For example, in this family, the square above the family indicates that Homer is the father, and the circle that Marge is the mother. The circles below show that they have two daughters, Maggie and Lisa, and one son, Bart. Similarly, Marge's parents are Jacqueline and Clancy, and her sisters are Selma and Patty. More generally, cells above the family icon point to the parents of the family, and cells below to the children. Cells on the left of individuals show which family they were born into, and cells to the right show in which families they participate as parents. In the Greek pantheon, for example, Zeus is a father in more than one family. He married Hera, with whom he had 4 children, and coupled with other individuals, including one from a different generation. We implemented the Junior Code visualization in an interactive genealogy exploration system. The system consists of a main visualization window, an overview, a query window, and a timeline. For this family of 700 individuals, we can use the overview to quickly pan across the genealogy, while the main window automatically zooms out to fit as much content as possible. At the same time, the timeline shows the time span of the main window. By selecting an individual, we can see all its ancestors and all its descendants. We can talk.
Okay, I think you get the idea. So this is a matrix representation that is a little bit unconventional because it's for a tree, but you can also do this for trees, of course. And so one observation about these matrix representations is that they are often very dense in certain regions, but then they have a lot of empty space essentially. And so conceptually you can of course then come up with a hybrid layout, as here node tricks. So here this is I think a co-author network, here grouped by Xerox PARC researchers, here collaborators of Ben Schneiderman, a famous infamous author. And so you see that the dense regions here are represented as matrices, and then connections that are outside of these dense clusters are made as links. So here is how you can interact with the system. If it loads. So by selecting a group of nodes, you can simply make them into a matrix. These are these densely connected clicks here. So the fundamental idea is that you kind of use the best of both worlds. Of course, you get some of the advantages of both worlds, but of course you also have this overhead of explaining to people what the embedded matrix representations mean. So what can we do about the screen real estate problem that we have quadratic screen space requirements? Well, one approach would be to, if we have a hierarchical structure that we can define, and we always can define a hierarchical structure artificially, for example using clustering, we can try to collapse these regions. So we could define, okay, this is one cluster, this is the other cluster, this is the third cluster, and then we can introduce these levels, and we can then aggregate those levels away so that we don't have to represent, for example, all of the elements down here, but we could show, okay, we could give this a shade of gray to show how many connections are within this group K here. So that would be one possibility to get around this. You can, of course, there's also a lot of papers that introduce interaction techniques for working with very large matrices and so on. Okay. Next I wanted to talk about implicit layouts for trees. And so I wanted to start this off with a basic sketch. So let's assume we have a tree like this. Okay, so we have a root node, and then we have two nodes on level 2, and then 2 more nodes on level 3. And so what a tree map does is it represents the whole tree, or everything that is a part of under the root, within this one space, within one square. And so like this rectangle here represents the node. And then we have like a division here into two branches. And so what this algorithm, or the idea here is that I simply divide this. And so now I represent those two here. Like this rectangle here would be this, or this rectangle here could be this leaf. This rectangle here could be this node in the middle of the tree here. And so since we have two more nodes down here, we will do the subdivision again here. Okay, so that's the basic idea of a tree map. Can anybody see any problems with that?
So at this point, I don't know if it's gonna be like this, but at this point, if the nodes have weight, you're not really taking that into consideration in terms of the area that's being used.
Yes. This is, of course, the next step then. Why tree maps are interesting. Like at this point, I only try to represent the topology, but I can vary the size of these nodes. So, for example, if I wanted to have every node here, like every leaf equal weight, or yeah, every leaf equal weight, I would probably move, like I'm guessing now, but I could move this over here. And now these are approximately equal. Now I have like an evenly balanced space for each of the nodes. If I had attributes, for example, this would be 5, this is 1, and this is also 5, then I could modify this accordingly and represent it like this. Any other, like let me draw a little bit more here. So how would I, like if I wanted to click on the root, yeah?
I was going to ask how you handle the difference between no children and one child.
Not well. Exactly one of the problems. So yes, that's exactly what I just wanted to get at. If you have something like this, there are ways of doing it, right? You could say, I have a certain amount of space reserved for showing the topology down here. Okay, something like this. However, it gets a little tricky, and most implementations actually don't do that. So if you just do the simple layout, you can actually not faithfully represent all of the topology. So what I'm getting at here is that these things are really great if you have something, for example, like a file structure on your computer, and you have like deeply nested file hierarchy, and some of, like, you have big files in some directory, but you don't know exactly where it is, right? By adding up like the directory, let's say this is 1, 1, and 3, the size of the directory is the sum of its children. So here we have 1, 1, and 3, which is 5. Then here we could have 1 leaf. This is 1. So in this case, I don't care so much about the topology. If I want to find large files, I care more about the attributes of the leaves. And so for exactly these cases, this is nice. In practice, what you can do, of course, is interaction. The same problem like that you have, it's hard to pick the root. And so usually most implementations, if I hover here with my mouse cursor, they would highlight this node, and then they would highlight an additional layer about that. Okay. So here, this shows exactly the idea. So here you actually preserve this information and this particular layout, this topology information, because you give space to, by not drawing it completely full, you give space to the hierarchy of the tree. But most implementations in most cases are like this, so you couldn't really distinguish between whether I have a leaf here, the root isn't represented at all, and so on. But these attributes for the leaves are easy to spot. Here is an example of a zoomable tree map. So this is a 2012 budget proposal, how 3.7 trillion is spent. And I could like zoom into any of these areas and then see the detail level. And so here, what I really care about is this like higher level structure, and then seeing, again, what we see here is the change compared to 2010, red being a decrease in spending, green being an increase in spending. And so if I go down here, I can see this is military personnel, family housing, and so on. You could make, this is like a purely geometric zoom. You could of course be a little bit smarter about the zooming here, so I could like select a level and zoom into that level and so on. So there's approaches like that too. This here is an example of an interactive tree map of 1 million items. And as any of these like pixel dense techniques, they're really good at scaling. Like 1 million items is really hard to visualize generally, but if you have these very structured layouts, it doesn't really matter that you can't see the details here because you can see the overview of all of this stuff. And so for both Mac and Windows and also for Linux, there are implementations that you can actually use to look at your file browser, to look at your hard drive. And so if you run out of disk space, this is actually, I always use a tool like this to explore where can I delete something that I don't need anymore. And so this is my Google Drive directory. Everything that I put on Google Drive is about 300 gigabytes of data or something like this. And you can see, like by hovering over here, you can see that, like on the one hand, this file is highlighted, but also it's containing folder. So like we have the folders actually up to a couple of levels. The whole hierarchy here is highlighted of all the contained folders. So this is how you can see the structure. The color here are file types, and the size is of course proportional to the size of the file. As you can see, it's hard to see for you, I guess, but this is a Windows Media video file. This here is a GoPro MP4 file. This here is another GoPro file. So GoPros create a lot of data. Here we have from this lecture the interaction slide deck because there's a lot of videos in there. It's very big and so on. So I don't really care so much about the hierarchy here. I care more about the attributes themselves.
What's that called?
This is Grand Perspective for Mac. For Windows, there's Sequoia View, and I don't remember the name on Linux. Grand Perspective.
What is the middle section? Are those your partitions? So it's defined into two very distinct squares.
Yeah, this is because my photos folder
Oh, I see.
here needs most of the space. So this is not, well, photos folder is a top level folder in this directory, but it's at the same level as, for example, this folder here, which are my wife's pictures, and then here are research projects. Here are proceedings from conferences and so on. And of course, like what is nice about this, then you should be able to reveal this in Finder and then look at the file and then delete the file. And these things are pretty like easy to use and accessible. So a different idea is to use another implicit layout. These are called implicit layouts because there's no explicit representation of the topology. Another idea of using these implicit layouts is this radial layout. So it will be more difficult to draw. But what we start off with here is like a circle that represents a node, and then we have two subtrees. Like this. So now this here is that subtree, this here is that subtree. In this case, again, I have like a leaf here, but here I will divide it up. Like this. in this case, it's like again an equal division. So what I'm doing is every level down, I'm deciding how much angle to give the subtree. And so here I'm again not like I'm giving every leaf the same angle, but of course I could vary the angle based, for example, on the number of leaves, the number of nodes, or the attribute size. So for example, if I wanted to say increase or do this based on the number of nodes, I would do something like there's or leaves, there's 1, 2, 3, 4 leaves, there's 1 leaf over there, so I would only give this here like a small space and extend this like this. And so this is how I then hierarchically, let me finish this, this leaf here has 3 nodes, so I would add another piece here, like that. And so this is the fundamental idea, that you like add a level of disks here and then code by angle something like the size or the size of the attributes or the number of leaves in that space. You can, D3 also comes with these layouts. So this is a zoomable example. Here's the root. And then I can click on any of those nodes and it zooms in. And I can click on this current root and go back out by a level. And so this preserves the topology better. But of course it's not as space efficient because I'm also representing the intermediate topology. And so for example, compared to a grand perspective or to a tree map, the space that each of these leaves gets is smaller. However, there are still, I personally like the Sunburst quite a lot. There is, for Linux, I know there is a tool for file size, it's called FileLite. I'm not aware of a Mac implementation for this.
So the Mac one is called Daisy Disk. Actually, that's the one I use and it does exactly.
Daisy Disk, okay. Here is an implementation that a student of mine did a while ago for this focus and context technique. So what you see here, oops, I want to hit pause. So what you see here is that, it's a little hard. The full hierarchy is like embedded in here. It's like made small and embedded, and the current selection here is highlighted in blue here. So the blue part here is what we see out here. And so this is like one of the possible focus and context technique here. So I can pop these out dynamically. And this also has like pretty fancy labeling and so on. This was implemented all in OpenGL by hand before D3. So it was a bachelor thesis. Nowadays, this probably should take you not more than 4 hours. Yep.
Is that a radial implementation where the roots node, rather than being in the center, is the all-encompassing? So it's similar to the grand perspective that we were looking at.
I'm not aware. I think it's an interesting idea. I'm not aware of an implementation or even a prototype. I guess an advantage of using it from root outwards is that you get more elements as you go down the tree. And if you get more elements, you need more space. And if you go inwards, you get less and less space. So the leaves don't have a lot of space left. But if you go outwards, you get more space the further down the hierarchy you are. So I'm not aware of it, but I'll show you a website later. If it's not on this website, it doesn't exist. But it might be a good reason why it doesn't exist, because of this inverse relationship of number of nodes and the space that you have. Okay, so if we look at the pros and cons of implicit representations, the pros are they're space efficient because of the lack of explicitly drawn edges. They scale well up to very large graphs. We can show 1 million leaves in a tree map, for example. They're usually well suited for attribute-based tasks in the node sets, because we can, at least if we talk about leaves, we can visualize node properties very well. Since they don't show any edges at all, they are not at all suited well for attributes-based tasks on the edges, of course. There is no explicit edge representation that we could use to encode, so they don't really work for that at all. And depending on the spatial encoding, they could also be useful for topology-based tasks. Tree maps less so than Sunburst, but you can easily navigate the hierarchy, at least with interaction. The biggest drawback of them is, of course, they can only represent trees. There are, let's say, prototypes of graph visualizations, general graph visualization that use this implicit representation, but I'm actually sparing you those because they don't really make sense and they're hard to parse. So the ones that we looked at, they only represent trees. They're useless to pursue any task on the edges, I already said that, and it can lead to occlusion of, for example, if we have a leaf that completely occludes its parent. So here's this website that I mentioned, the tree visualization reference. This guy collects every tree visualization ever published. He does not curate them, so there is even very, very crazy stuff in here. And as you can see, there's a lot of them, they're still loading. So here is a 3D exploding sunburst wheel, for example. Or here is some 3D polar step tree, or some cylindrical, or a sunburst sphere, or organic tree visualization. And all of this is referenced, so you can like access the papers and cite them. Here's the cushion tree map, which is kind of the cushion tree maps. Is this tree map algorithm that does this nice shading and rendering where you can easily distinguish the rectangles. This is what Sequoia View, this implementation from the TU Eindhoven uses. So this is actually a tool that you can download and use. This is like one of the original Sunburst implementations, which is called information slices, and so on. And so here's the original Sunburst implementation from John Sasko. So if you're interested in trees at all, this is the ultimate reference. And then you can also filter them here based on dimensionality. So now I'm looking only at the 3D implicit representations, for example, and alignment. Yeah. Okay. So let me see. How much do I have left? Good. So one of the big problems in the open research areas in visualization is graph comparison. So if we have graphs that change over time, for example, a social network that evolves, how do we show these kinds of things? There's a couple of different approaches that you can do that. I'm not going to talk too much about it because it's a pretty special topic, but it's an interesting research area to work in. So you could do animation, for example, map that over time, but we know that mapping it over time isn't really efficient. You could do layering in 3 dimensions, as it's done here. You could create a supergraph and then have some explicit encoding of edges and nodes based on timestamps, or you could do aggregations and so on. So all of this would be possible. It is a hard problem, as we saw in the tree comparison example for when we looked at the phylogeny tree. It is not easy to do this. Then I wanted to say a little bit about visualizing edge attributes. So generally, edge attributes, they're often visualized with width. However, width isn't very expressive. So it's hard to see like a lot of variation. Basically, by varying edge width, you can maybe encode 4 or 5 different states, but it's not like length that we can easily see that because we have a very limited space that we can vary in. Then saturation would also work, of course, or some stippling, some styling is another possibility of visualizing edge attributes. If you want to work with large graphs, you also need to usually interact in some way with them. So there is like standard techniques with overview and detail. There is also edge-based traveling. So for example, if you zoom into a network and it has an edge that connects to another part of a network that is currently not visible, you could click on the edge and get a transition dynamically to that edge. Yeah, and so there's other methods here, this radar view for set planning and so on, but it's a little bit academic, let's say. One other thing that that is interesting to do in graphs is, of course, details on demand. So you don't actually have to show all, like for example here, this is the network originally, and then here we show only the edges that are incident to the two nodes, to the node inside. So like we defined a lens, and so now we only see the edges that connect to that particular node. So these kinds of interaction techniques can help you with working with larger networks. A couple of words on graph tools and applications. Of course, you can implement everything in D3, but if you just wanted to visualize a graph quickly, there's three major tools, two of them that I can definitely recommend. Gephi is one of them. This is a general graph visualization technique that reads a lot of different file formats. So you can download this as a Java-based application, and then can create graph layouts, can calculate a lot of graph measures with it. So if you just need to like visualize some graph, this is the way to go. If you are in the biology domain, you probably have heard of Cytoscape. Cytoscape is kind of the standard tool for visualizing biological networks. It also supports a lot of different layouts and a lot of different measures. It has a lot of plugins. So I think it has hundreds of plugins. And so here we see a protein interaction network, and where there's some color coding on the nodes based on some attributes. So this is like another downloadable tool. Cytoscape has a web version now, which is kind of compatible to some of their file formats, but not necessarily feature equivalent. If you are interested in a little more computational approach, for example with Python, there's a couple of Python libraries like NetworkX, which comes with a lot of graph algorithms, not so great graph visualization, but still very useful. And what I didn't put in here, but what is also increasingly more common is graph databases like Neo4j. Neo4j, like you don't have like big graphs, you cannot really hold them in memory. So you need a graph database, and then Neo4j also defines a query language that is similar to SQL conceptually, but it's called Cipher query language, so you can query for neighborhoods and so on. So if you need like a real-life graph project, I would probably recommend nowadays that you use Neo4j for that. Okay, so for the rest of the lecture, I prepared this redesign exercise. So we've talked a bit about The Simpsons today already. Here is a simple data set. We have Simpsons characters, Lisa, Bart, Homer, and Mr. Burns. And then we have attributes about them, for example, their age. And then we have characteristics or sets. So for example, Lisa is in school and female, Bart is in school and male, Homer works in the power plant and male, Mr. Burns is evil, works in the power plant and male, and so on. And so we have these attributes that we can treat as sets. And so how do we visualize the overlap between these sets? For example, we want to see, is there a correlation between power plant and evil? We can visualize this with set visualization, or specifically with Venn diagrams. And so I'll let you look at these Venn diagrams while I hand this out, and think a little bit about them, and then we'll continue from there. Oh, and there's a part of the sentence missing here. So this should say what marks and channels are used. Take a look at those two charts, compare them, think about how they're different, what marks and channels are they using, do both of them work equally well, what are the differences, and so on, and then we'll discuss this in a couple of minutes.
Are they both representing the same data?
No. So the one here is a 3-set Venn diagram. Both of these are actually representing genetic data. So this here represents, I call it the banana Venn diagram. This represents the banana genome and how it relates to the genome of 5 other plant species. So how many genes are shared between the banana and others. And this up here, I think, is co-mutations and mutations in these 3 major genes. P10, EGFR, and TP53 are known cancer genes. Okay, so let's first talk about the simple 3-set Venn diagram. What are the marks and channels used here? What's that?
Circle.
Circle, yes, that's the mark. So each set corresponds to one ellipsoid, I guess.
Hue and area.
Hue and area, yes. What does the area encode?
The size.
Intersection. Okay. And the hue is kind of like implicit encoding of these combinations, so we can kind of understand that the mixture of blue and yellow is green and so on. What's the value of the labels here for the left one?
Which labels do you mean, like the P1087?
Both.
So let's count.
Well, the string is just the indicator of the name of the gene, right?
Exactly. And the number?
Is it the number of mutations?
Yes, or the number. In this case, the number of patients, but it's the size of the whole ellipsoid or circle. And then what do the white labels mean?
They're the value of those subsections.
Exactly, of these intersections. And strictly speaking, are these numbers really necessary?
I mean, area is a tricky visual channel. So like 5 to 19, for example, it's hard to really tell what the ratio is.
Yes.
Maybe they're helpful.
So yes, they're helpful, but what I'm also trying to get at is one of the differences between this, the left one, and the right diagram. How are these shaped?
The areas are actually redundantly encoded in the number.
Exactly. So this is an area proportional Venn diagram. Whereas if you look over there, is this also area proportional? Yes. So let's take a look at this banana Venn diagram. Can you easily trace, for example, what a combination of the green plant and the pink plant with no other contribution is? So if I want to see the intersection of Brachypodium ditachon and Sorghum bicolor, it's pretty hard to do, right? Can you find it? So you have to think about this quite a bit. What do you think is the main difference between those two charts? Both use the kind of same encoding?
I think the left one is meant to be, it has specific information and gives you a good picture of overall how the data is related and what's going on. And our banana Venn diagram is mostly saying, well, there's this big area in the middle where they all intersect, and then there's some numbers. So trust us, we have good information here, but don't really worry about it.
Yes, so it's more like general idea, but don't try to read this in detail. Yep.
One of the things that really annoys me about the banana diagram is that you have these, well, in the center, you have these three semicircles. And the origin of them is all in the center, whereas on the left one, the origin is based on the intersection, and that I feel like helps a lot more to kind of visualize the data.
Yeah. So why don't you think that they do like a nice area proportional Venn diagram for this one?
Is it because there's so many groups? There's so many sets?
Yeah. So it is hard. It is basically impossible to visualize a complete, like to use a convex shape to visualize more than 3 sets in a Venn diagram. So it is really difficult to do for more than 3 sets, and so that's why you have to come out with these non-convex shapes to show these relationships. So who would say that this is a good chart? Okay, the majority. Who would say that this is not or this is a good chart? You kind of like it?
I don't really like the chart, but I understand that the data set's complex enough. There's not really a lot you can do to do tons better unless you say we're going to chop this and only look at a piece of the data set, and then we'll look at a different piece in a different
Well, I'm challenging you next to do that. To make it better in the redesign. Yep.
You could do like a matrix layout.
Let's not discuss solutions now. This is the next part of the exercise. Okay, so if you look at those, what you can clearly see is this is easy to read because we have a very contained data set and we have a very immediate, a very fundamental understanding of what we want to see here, because sets are something that we are taught in high school like this. You don't have to explain somebody that this here is the intersection of the green, of the yellow and the blue one. This is very, very clear here. By the way, what Gestalt principle is used here? Why do I assume that this is one shape and not that this here is the shape? Exactly, so I'm using this Gestalt principle of continuity in sets. Okay, so let's do a little bit of an experiment here. This is exactly the same Venn diagram. You can use this Euler ape tool to create those. And then if we split those apart, as you mentioned earlier, it is really hard to judge the size of these irregular shapes. So who thinks that the left shape here is bigger? Couple? Who thinks the right shape is bigger? Nobody? Just one person? You have a good angle for this. So it turns out that the left shape here is bigger than the right shape, but it's tricky to do. And so if we look at this diagram in a little bit more detail, it is not at all a visualization that uses somehow encoding to show the magnitude of the data. So up here we have a segment that has 1,151 genes and only a couple of pixels, and right next to it we have a segment that has 40 genes, exactly the same size. And down here we have a gigantic segment with only 105 genes. So this is not a great visualization technique. It is unfortunately not an isolated incident. This is from a major Nature paper, but it actually, here is the genome of trees, this is of mice, here is, mouse, human, yeast, worm and fly, and so on. So you can take a look at those, but now what I'd like you to do is to fix this problem. Here I kind of clipped some of the information, but you just flip your page and do this redesign exercise. So you should now take the spare paper that we handed out and create two alternative designs that fulfill some of the following criteria. You don't have to do all of them, but you should try. You should be able to easily see which sets participate in the intersection. You should be able to easily spot which is the biggest intersection. You should be able to easily see how large the overlap between pairs of sets is, and your design should work for more than 4 sets. And you shouldn't try to use a Venn diagram. So I'll give you 10 minutes or 8 minutes to sketch a couple of ideas. If you want to, there's a data set down here that you can use to play around with. But it's not strictly important. Who's having troubles? Anybody need any help or ideas?
Yeah, and you could have it, so like the name and each of every one number for each person, and then one number for each set.
Yeah.
And then you could click on the bubble, really want the connections or something.
Yeah, I've seen something like this for actors versus movies from HBO or HBO shows. Can I take a picture?
Yeah, it's very detailed.
Oh, you can see it here. Okay, thanks. Okay, so let's talk a little bit about, this is not an example that I picked at random, and it's also not easy. Like who is satisfied with his or her solution? two people. Who had trouble finding a solution here? A couple of people. So yeah, this is not an easy problem, and there's been a lot of work on this. I will give you a couple of examples of what people have done, including one of the things that I did myself. But this is not, you don't have to expect something like this on the midterm, because this is really like a tricky problem. So one way of potentially doing this is this layout here, where you present each of these segments as a bar, and then plot a bar next to it. Is this a good layout?
No.
No, because we have no idea about where it's from, so we would have to have the Venn diagram next to it to actually see what is going on, and so on, so this is not a great solution. You could create an overlap matrix, right? So you here, this is kind of like three sets, and here we have kind of the same data set, but more of them. So here's TP53, P10, and EGFR, they're all contained in here. But what does that show us? It shows us only the intersection between a pair, right? It doesn't show us any higher order intersections. What is the benefit of this?
For pairs, it's easy to determine.
Exactly, for pairs it's easy, and it works pretty well because we can in this matrix we can simply plot a lot of elements. So that is nice if you really don't care about higher order interactions, and it's very scalable. Another idea is to represent this, and this is kind of like a paper from myself and my collaborators on this problem, that we represent these intersections in a matrix. Right? So we take this apart and say, okay, here's the set A, here's the set B, here's the set Z. This is the row that is not A, not B, not C, so this area outside of the Venn diagram. This is A, not B, not C. Well, it's not labeled here, but it's this area, 17, and so on. And so here in this matrix, we can kind of define dynamically. We can map every intersection, and then we can plot this as bar charts. So the advantage of this is that it works for more sets. One of the disadvantages here clearly is that it's not as intuitive, right? So you have to learn a visual encoding. You have to learn how to read the matrix. What is nice about this is that you can also use the space. For example, if you wanted to plot the age of Marge and Lisa and so on, of the Simpsons characters, you can actually plot additional plots here on the right. So we're doing this here for like aggregate attributes or even like some statistical measures about the sets and their sizes. So if you want to play with this, you can go to the website, and I think I've shown this to you guys before, vcg.github.io/upset. And here is an interactive version. And you can actually look at the Simpsons data set like this here. Then I can sort, and then I can see that the biggest intersection here is people that are Duff fans, male, and work at the power plant, for example, and that's Homer, Lenny, and Carl. So this is one example of doing this. There are other examples. By the way, this is the banana Venn diagram with this kind of approach. So here, it is still not an easy chart to read, but you can very quickly see that by far the biggest intersection here contains all of these plants. And the second biggest intersection contains these three. So there is like, these are more closely related to each other than to the rest. And then the third biggest intersection contains these five. So the Phoenix bacteria, which is a date, as far as I know, is kind of like the odd one in this set. And so here you can like read the data and you can actually like just like reason a little bit about some patterns in contrast to the banana Venn diagram. There's a lot of other options that people have published over the years. Here at this website, setviz.net, redirects you to this other website, and then you can see here like a postcard that has these various visualization techniques here. And so I've seen one of you back there has come up with this decision tree-like approach that somebody else is already taking. And you had this bipartite graph approach, which is already also in here. So these are various options. Like here's another bipartite graph layout. These are various options for set visualization. Some of them are good for certain techniques, for certain problems, for certain data sets, others not so much. So if you're interested in this, I recommend this website, and there is like a review paper that also discusses all of these techniques. Okay, that's it for today. I'll see you guys on Thursday.
Hey, I know you messaged us about our project, but I can't find it. Did you email us or?
No, I was just comment on the submission project proposal.
Oh, okay.
Yeah. Are you not able to see that?
No, I was. My teammate just sent an email that we didn't get like a response from TA, and I was like, I'm pretty sure I saw you contact us.
Yeah, I
somewhere.
did. I added it like a week ago, I believe. So is that your email?
No, they're none of them. Also, is it possible to change our categories?
Yeah, that should be fine. Just because you have my email ID, yeah, you'll have to communicate that with me.
Okay,
Yeah.
sounds good.